Good morning, good afternoon, and good evening, everyone, and welcome to today's Ask the Expert webinar on X-ray diffraction. Our expert for today is Stephanie Williams, one of our XRD scientists here at Eurofins EAG Laboratories. My name is Rena Samsu, and I am the Senior Marketing Manager assisting with today's event. Before we get started, I would like to go over a few housekeeping items. All attendees have been muted. However, if you have additional questions that come up during the presentation, please submit them in the questions section located in the bottom of your control panel. You may send in your questions at any time during the presentation, and we will follow up with you in the coming weeks. With the abundance of questions submitted for today's event, we unfortunately will not be able to get to all of the questions during the presentation, but for any unanswered questions, the team will try to send answers out to those questions in the few weeks following. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. Now I will turn it over to Dr. Stephen Roby, who will be moderating today's presentation. Steve?
Thanks, Rena. Good morning, good afternoon, good evening, everyone. My name is Steve Roby. I'm the manager of EAG's X-ray group in Sunnyvale, California. I've been doing X-ray diffraction since the Stone Age, but for the last 14 years, I've been working at EAG. Joining me today is Stephanie Williams. She comes to us from Notre Dame University. She has over 5 years experience in X-ray diffraction, including single crystal diffraction, high pressure diffraction, and synchrotron diffraction, and is the go-to person if you want to know anything about how to make buckyballs out of uranium. Before we start, just an agenda, the agenda that we're going to follow today. Stephanie, if you can give me the next slide, thank you. Just a little bit about the company, then we're going to talk about the smart chart and then get into the questions. Next, yeah. Eurofins is a global leader in testing with more than 58,000 employees, 900 labs operating in 54 countries. Eurofins EAG is a division of Eurofins, and we specialize in materials testing with over 40 years of experience. We have over 1,000 highly educated employees operating in 20 laboratories. With more than 2,500 different analytical tools, and we support more than 5,000 clients. For the purposes of XRD, there are 2 XRD labs, our lab in Sunnyvale, California, and another one in Eindhoven in the Netherlands. All X-ray work from the rest of the world comes to one of those 2 labs. So without further ado, take it away, Stephanie.
Okay, thank you, Steve. So we received hundreds of questions, and I'm going to do my best to answer as many as I can specifically, but what I found was a lot of people had the same questions. So I've tried grouping these slides based on people that had similar questions, and then we're going to go over some basics and some group kind of answers to talk about more of the theme of the questions versus one-on-one. So a lot of people asked, how does XRD compare to this other technique? So it sounds like a lot of you might have had these other techniques that you work on. You may not be in XRD, but you work with EBSD or DSC or SEM or other microscopy techniques. So when we look at how XRD compares, this is called a smart chart, and Rena is going to post a link to this, or you can use the QR code to get to this actual figure. And SMART is an acronym for Spectroscopy, Microscopy, Analytical Resolution Tool. And it allows you to compare spot size and detection limits for all the techniques at EAG that we can offer. And so the x-axis is your spot sizes, which is here, and here is your detection limit. And then we can see that XRD and XRR is in this top right corner. We also have these kind of straight bars over here for the bulk techniques, and then the imaging techniques down at the bottom. So this is a very good chart to compare your technique of interest to XRD and see how that lines up. The other thing we can look at is the depth of analysis. And so, for example, TOF SIMS has a very shallow depth, but XPS and Augur have, more depth that you can penetrate into the sample. but the arrows indicate that deeper depths are available by depth profiling, but not necessarily a standard technique. So again, over here, you can see the XRD, we can probe, you know, top surface to down to bulk substrate material. Many questions came in saying, you don't know anything about XRD, you want a deeper understanding of it. And that's great. I'm super happy for everyone here that just wants to know a little bit about what X-rays are and what X-ray diffraction can do for you. So we're going to start from the very beginning, the X of XRD, X-rays. So everybody remembers the electromagnetic spectrum from school probably. We've got X-rays up here on the higher energy end, past ultraviolet light. And X-rays are used for a wide range of things. I'm sure everyone's gotten some kind of X-ray at some point in their life. You know, we use it at the airport to scan our bags, and we use it in crystallography. So one of the most important things to know about X-rays is the idea of constructive and destructive interference of waves. So first, this is an example of constructive interference. When the waves are aligned, it actually produces a higher signal than the two individual waves by themselves. Destructive interference is if the waves are actually offset from each other, you'll get less or no interference. So this is what is going to essentially make Bragg's law, which is why diffraction happens and the relationship, the mathematical relationship of why diffraction happens at certain angles for certain crystallographic structures happen. So let's say we have a lattice and we have spacings D. So that D spacing is the area between a lattice plane or in a crystal structure. So those dots are not necessarily your atoms per se. Now we have X-rays that are coming in and out. So the incident angle is on the left and then it's scattering out. And if we think about, you know, this is one wavelength from peak to peak or valley to valley, and then we add more X-rays. So these X-rays are going to create diffraction because if you kind of draw a dotted line down from the incident and the scattered, you can notice that in each successive layer down, you have to add half a wavelength on each side, or essentially one full wavelength, to make sure that the waves are in line with each other when they scatter. So you notice for the next one, there's a full wavelength added on each side. And if we draw a triangle here, we can look at it and know that this is theta, which is the angle between the incident and scattered beams. And if we pull this triangle out, I promise this is one of two math equations you're going to see all presentation, but we know that this length is D, we know that this angle is theta, and we know that this length here is lambda over 2. So from trigonometry and SOHCAHTOA, we know that the sine of this angle is the opposite over the hypotenuse. A little bit of algebra will get you to n lambda equals 2d sine theta. So this is the equation that gives you the relationship of why theta relates to d spacing and your wavelength and what causes diffraction. A lot of diffractometers you're going to see have a typical geometry called Bragg-Brentano geometry. And what that means is that the source on the left side and the detector on the right side are going to move symmetrically to each other on what we call this Bragg circle. And what that is going to do is it's going to analyze any planes that are parallel to the surface of the material, because that's, again, we need those lattice planes parallel to create those constructive interfering waves of X-rays. So now that we know a little bit about X-rays and what a diffractor is going to give us, a lot of people wanted to know details about our specific instruments and some differences between them because different companies make different instruments. And we actually have 9 diffractometers in our lab from 3 different companies. And we have one that most of our instruments are copper radiation, but we do have one that's cobalt. Cobalt is very good for iron-rich samples, which are very, fluorescent essentially, which it can lower a fluorescent signal so that you can see your diffraction better. We have all different kinds of geometries, parallel beams, symmetric scans that we can do depending on what the sample requires. And we also have some small spot diffractometers as well. So this table here is just a quick summary of the types of instruments that we have, our specific sources, the powers, and the actual, types of detectors that we have, which I also failed to mention that we have anything from a point detector, which is 0D, to we do have 2D detectors on 2 of our instruments as well. Lots of people want to know about micro XRD. How small of a spot size can I probe? How little of a sample can I have and still get diffraction information? So our smallest spot size is 25 micron. And this is actually a D8 Discover that we have with a Vantec 500 2D detector on it. So this is our 2D detector. And what that's going to do is with a 2D detector, you can actually get more grains into diffracting conditions, so your intensity is improved. Now, with this is focusing geometry, and so we can't do anything like grazing incidence, XRD or XRR, and there's no monochromator on this diffractometer either, so we can't do high resolution. So our answer was to get a new diffractometer. Now, this micro high resolution HR Rigaku Smart Lab has very special pieces to put it all together. So if we look inside, there's actually several things that make this instrument very nice. And there's only 2 of these in existence. One is in Sunnyvale, California, and the other is in Rigaku's lab in Tokyo. So if we go through the 5 things that make this instrument really nice, the source is a high brilliance microfocus rotating anode. So we've got a beam footprint of about 70 microns to start. And it's very, very high brilliant, but it doesn't take a lot of power. Very high brilliance is going to help you with small spot sizes because you're not losing your intensity of your beam by cutting it down. It's already intense at a very small footprint. With the mirrors, we have a confocal max flux mirror. This produces your X-rays parallel in both the meridian and the equatorial directions. That's going to allow you to do your grazing incidence, your XRR, and things like that. We've got a full XYZ, chi and phi motion rotation stage on the sample holder, so we can move and manipulate a sample in any angle we need to get information off of it. We've got a variety of slits that allow for, again, grazing incidence, high resolution, all kinds of things like that. And this is one of our instruments with a 2D detector on it. So you can operate it in 0 and 1D modes, but again, that 2D detector is really nice for getting better counts, better intensity, and getting diffraction spots that you may not necessarily see if you're using a point or a line detector. Many, many people ask questions, can you run this X sample? And the answer is yes. The more important question really is, what kinds of information can I get from the analysis that I can run on my sample? So this is a little word cloud. If you see your word on there, awesome. I basically tried to collect as many times people ask questions about specific types of samples. And as you can see, a lot of people really care about thin films, which I promise we'll be getting into lots of details about thin films later in on the talk. So now some people asked about sample preparation. So with thin films, you're not really preparing anything. I mean, you prepare it and we take it and we're going to run it as you made it. There's really not a lot of things you can do there. But with powders, there's a little bit more, because essentially in a powder collection, you want as many randomly oriented crystallites because you want to get reflections from the way the crystal is moved around all of the angles. And so there's several ways you can do that. So if you have crystals that might necessarily like pack down flat, you can do what's called backloading. So this is just a piece of metal with a hole in it. And if you tape a piece of glass to one side and then pack this in, then tape a piece of glass to the top, flip it and take the back off, that now becomes the front, it's called backloading. And that can give you more orientations of crystallites than if you would have just top loaded and packed it down. If you have a very small amount of sample, we can do what's called zero background holders. So we just kind of dust it lightly on the surface of the silicon. And then when we dust it and shake it off and then dust it and shake it off, we're hoping that the crystals fall in all different kinds of ways. This is another example of a zero background sample holder. This is a typical glass slide where we would load top down. And there's all kinds of other ways to prepare your samples, grinding with a mortar and pestle, using a sieve to make sure that your crystallites are smaller in size. This is an automatic sampler, but also a sample spinner. So spinning your samples or tilting or rotating your samples to move it while it's being collected will also up your possibilities of getting different kinds of diffraction angles. So what can XRD do? This is where I was saying we're going to get into the actual analyses that you can do with diffraction and what actual answers you can get. Now, a lot of people asked about specific, how would you analyze this in this kinds of software? And we don't really have the scope of this presentation to go into actual working with software. I can tell you that in our group, we use Jade, which is from, materials data. And this is a really nice program because it works with any data from any kind of brand of diffractometer versus having a diffractometer specialized, brand where like Bruker has EVA and Rigaku has SmartLab and things like that for the analysis. This you can use any kind of data in it. So first, most simple kind of qualitative information you can get is what's in my sample. And to do that, we need to have databases. Now, for the database that we use the ICDD, and this has about 500,000 entries in it. So again, I was mentioning those diffraction peaks. Now, in this example, we've got two types of phases. We have a corundum and a titanium nitride phase. And because these have different crystal structures, the diffraction peaks will show up at different points in 2 theta. So we use XRD like a fingerprinting technique. And what we do is if we know some of the elements in the sample, we can restrict the database search by those elements. So it's not searching all 500,000 compounds in this database. And that's something important to remember is that XRD is structural, it is not elemental. So if you have 2 compounds that have the exact same structure, but the atoms in the structure are different elements, the peaks will show up in the same spot because it actually can't see what element it is. Next, we have pharmaceuticals. So this is something that a lot of people wanted to know about. Now, this may have the same chemical formula, but they have different crystal structures depending on how the molecule is packed into the structure. And different polymorphs of pharmaceuticals are either active or may not actually work in the drug. So for pharmaceutical industry, it's very important to know which polymorph of the drug do you have. And for an example, this is astaxanthin, and these are the 2 polymorphs of astaxanthin in the database. And the blue lines are polymorph 1, and the red lines are polymorph 2. So can we see different polymorphs? Yes, and this is something that's very important to think about. The other thing we can do analyses where it's in different excipients. So if it's in a pill with other add-ins or a cream or a lotion or, any kind of thing like that. The thing that helps us is that if we have the plain API or active pharmaceutical ingredient, the mixture of the API and whatever the substrate that it's mixed into and just the placebo without the API in it, we can compare those to make sure that the peaks you're seeing are only from your API and nothing else is there. Next, after what is it, the next question is how much is there? And our typical detection limits are plus minus 5%, weight percent. And again, this only works if you know all of the compounds within your sample. So in a quantitative phase analysis, there's several kinds of analysis you can do. You can do what's called, direct derivative, which is you're purely using the area under the curve essentially, and you're saying there's this much area for these peaks with this phase, and there's this much for that phase. And that's, a good back of the envelope. A lot of people ask about rebuild analysis, which is essentially using least squares refinement and knowing the program doing the refinement knows the actual crystal structures. So it's refining the peak intensities relative to each other, the peak widths based on crystal light size, and there's a lot of other basically variables that you're refining to make sure that you are getting the correct percentages. So this is that same pattern that I showed before, and you'll notice this very broad peak is amorphous material. So we can't tell what the amorphous material is. I know what it is, it's glass. So I knew what the exact density is. And if you know that all of your amorphous material in your qualitative phase analysis, or your quantitative, if you know it's all the same amorphous material and you know the density, you can do quantitative phase analysis with amorphous material. If you have more than 2 types, if you have more than 1 type of amorphous material, it's not going to give you any kind of realistic kind of answer in terms of percent weight and quantity. Next is percent crystallinity. How much of that is amorphous and how much is crystalline? Now, when you're calculating this ratio, what it really is it's just area under the curve. So we have to know essentially how broad the peak is. And similarly with profile fitting, which is what we do for percent crystallinity, it's also how we're going to calculate crystallite size, which this is the second math formula that you're going to see today, and the last is the Scherer formula. That's the formula we use to calculate crystallite size. So this is percent crystallinity and crystallite size. This is the same data again, except this time I've profile fit. Now what that means is that I have an individual profile that's refined the shape of each peak, and we take the highest intensity, least overlapped peaks from each phase, and we can calculate that crystallite size, and then we average those and report it with the average and the standard deviation. So in terms of a statistical analysis, that's what kind of statistics you're going to get on that. And the crystallinity of the sample is 47.0%, which again is the program said, okay, this much is crystalline and this much is amorphous, which means this percent has to be crystalline. And that's just a calculation that Jade can do for you. This QR code is actually a blog post that EAG did explaining more about, what's crystalline and what's not crystalline for, future reading. A lot of people want to know, well, can I analyze just the top surface of my sample? And the answer is yes. This is called grazing incidence. So we have a fixed incident angle, but we scan over 2 theta. And what that's going to do is because we know the incident angle, and if you know the density of your material, you can calculate how far into the sample you're penetrating. And next, we're going to talk about texture. Now, there's a lot of ways to analyze texture. Now, for texture, you want to, this is not roughness of the actual surface of the sample. This is orientation of crystallites, is what we talk about when we talk about texture. Roughness only becomes a problem with the texture measurement when it's on the order of the spot size. So essentially, if you have roughness of 50 micron wells, but your spot is also 50 microns, you're going to have an issue with terms of trying to get enough crystallites to get the actual information from the texture that you need. So the most simple kind of texture analysis we can do is just preferred orientation, where the database phase is calculated based on the crystallites having perfect random orientation, whereas your sample may not be like that. And we can compare the ratio of the peaks in your sample to the ratio in the database and give you which direction in H-scale is your material preferentially oriented. So in this example, we have preferential orientation in the 111 direction. Rocking curves can also give you a lot of information about texture. So for example, if you have a peak with a material X that has a 2 theta peak at 38.2 degrees, and you want to measure a rocking curve, what you're going to do is you're going to fix your 2 theta, and you're going to scan omega. And what that does is we're going to scan over half, because omega should be half of your 2 theta. So in the case of 38, you're going to be scanning somewhere around the range of plus minus 2 in the, I believe, 17 2 theta area. So in the case of a rocking curve, what this is going to tell you is that if you have a very broad rocking curve, that means that you have very little texture or no texture in your sample. But if you have a very sharp peak, that means you're very textured, because all of the crystallites are pointing and in that same exact spot in omega. And again, that's how the omega curve collection is going to work. So next we're going to talk about pole figures, and I'm going to hand this off to Steve to talk about.
Thanks, Stephanie. Sometimes the texture is complicated enough that the peak ratio method or rocking curves doesn't give you a complete answer. An example of that might be something like when aluminum metal is rolled into a sheet. So in this case, we use pole figures. This is this technique can measure texture with any kind of texture, any fiber texture or more complicated ones. And the way this works, Stephanie, if you can go to the next page. So we're going to do at each angle, we're going to do a full 360-degree scan in phi. So we're sitting at the X-ray, the peak location of the peak or the plane that we're interested in. We're fixed at that position. So in this case, the 001 location, we do a scan in phi, we tilt the sample 5 degrees, we do another 360 in phi, and you gradually build up a pattern. So if you have something like a cubic phase like these two, you might have fiber texture where the 100 peak is at the center, and then there's basically no intensity until you're at 90 degrees. Whereas if you were looking at a pole figure for another plane, a 111 plane, you would not see any intensity until you get out to an angle in chi that's equal to the interplanar angle between the 001 and the 111. So you basically, from putting several of these pole figures together, you can get a three-dimensional picture for how the grains are textured in your sample. Back to you, Stephanie.
Thank you. Okay. So we also got some questions like, how can missing peaks corresponding to some planes not observed in an XRD pattern be observed? And one method of doing that is what's called in-plane measurements. And so what that does is, instead of, doing our typical collection in plane, or well, I would say parallel or perpendicular to the plane of the surface, we want to collect the planes that are now facing this way. And so we swing the X-rays. Come on. There we go. We swing the X-rays and the detector in the plane of the material. Now, another thing that's happens that a lot of people wanted to measure was residual stress. And in the most typical residual stress measurement is a sine squared psi method. And so what's happening here is we're looking at tilt with respect to the surface, which is technically the chi physical axis, which is the tilt of your sample. And the slope of the line is the function of stress elastic modulus of the material and the Poisson ratio. So again, when you're looking at these, in this tilt, the green crystals are diffracting. In this tilt, the blue crystals are diffracting. And in this tilt, the orange crystals are diffracting. And so what that gives you is that, for example, in this material, the D spacing 2 theta peak is going to shift with respect to the stress. And it's more sensitive to this at higher 2 theta. So we're going to look at this peak out here at about 130. And what we can see is that at different tilts, the D spacing position is at a different value. And each of these values is plotted with respect to the tilt, which is the sine squared psi. And what you get is that slope. So like I said, if you know your material, you know the elastic modulus and Poisson's ratio, which means we can calculate your residual stress. In the case of this sample, it was 2.17 GPa. Now, the next thing is, this question came in, some alloys are not chemically polished. How do you overcome chemical resistance of some superalloys in order to do depth profiling of residual stress? Are there alternative methods? And yes, so by chemically polishing, I'm assuming what this person meant was that we're applying some kind of chemical to strip a layer, then do residual stress, rinse, repeat. We don't actually need to do that if we're using grazing incidence sine squared psi method. So in grazing incidence, remember, we have this fixed incident angle and we're rotating and moving our detector. So in this case, the detector's here. So we are actually measuring the planes, the blue crystal planes. Now in the orange orientation, we're actually seeing the planes of the orange crystals. And in this case, if this is actually flipped 180, which is the phi sample rotation axis. And if you flip it 180, you can actually get the reflections from these green crystals as well. Now, in this case, what we're plotting is the shift of each different kind of peak is going to shift in relation to each other because of, again, the stress. So what we're doing is the lattice, if you calculate the lattice parameter from each of these, it's going to be different based on where we've collected it, because essentially we're moving the detector, not tilting the sample. So these angstroms are your lattice parameter, and then we're going to again plot that with respect to the tilt of the sample to calculate your residual stress. Now remember I said that if you know your sample, you can calculate how far into the sample you're penetrating. So we can calculate this residual stress for a certain incident angle, change the incident angle, and then report residual stress at different depths into the surface. So in the case of this sample, we've got, almost no residual stress at the surface, but as we penetrate into the sample, we increase our residual stress. Next, we're going to talk a little bit about high resolution XRD. And again, Steve is going to talk a little bit about these questions.
Okay, so there are a lot of questions that came in about the crystal quality or how do you measure defects. The first thing we have to do is talk about what's the difference between high resolution XRD and normal XRD. A normal XRD source is polychromatic, so even though you're looking at copper K alpha, you're getting a continuum of X-rays as well as K beta coming out of the tube, and it's divergent. And for high resolution diffraction, you need to get to where you have only a single wavelength, in this case, copper K alpha 1, and it's parallel beam. So you go through some kind of monochromator to do that. That's going to reduce your peak widths from, say, on the order of a couple of tenths of a degree, 2 theta, to a couple of maybe 10 arc seconds, so 0.003 degrees, much narrower peaks. Once you do that, you can do a rocking curve like Stephanie talked about earlier. You sit on a particular diffraction peak and you scan the diffractometer in omega and measure how wide is the peak. The defects, dislocations will broaden these peaks. Sometimes this is implant damage, sometimes it's strain in the crystal is causing it, sometimes it's mismatch between the substrate and the film, which causes the film to be under high stress, and it will create dislocations to relieve that stress. But basically what you're going to do is measure the width of the peak, subtract out what the instrumental resolution of the peak, and the broadening that you get is going to be a function of the dislocations. All right, Stephanie, back to you.
Thank you, Steve. So now, a little bit more into high resolution XRD. We're going to talk about the reciprocal space maps. So what provides more information, a reciprocal space map or a 2 theta omega scan? So reciprocal space maps are actually a compilation of many 2 theta omega scans. And what that's going to do is it's going to give you information about either strain or composition or both. So for our example today, we've got a silicon germanium thin film on the left. Now, we know that the thin films in these examples have the exact same composition. So we know that the layer peak here is shifting because of strain, not because of composition. In this case over here, we have an aluminum gallium arsenic film, and we know that the strain is the same in all these cases, but from blue, we have 100% aluminum, and in purple, we have 25% aluminum. So we know that the shift in this peak versus the substrate is because of composition. This is a symmetrical reflection. Now, in order to deconvolute the change of the peak shift in a symmetrical reflection, you have to move to an asymmetrical reflection and do the reciprocal space map collection. So we're going to use a multi-layer silicon germanium thin film for the example. And this has 9 peaks plus your substrate peak. And this was about a 1.4 millimeter spot size. Again, we don't know why these peaks are shifting. We don't know if these layers have different compositions or if they have different stress. Now, these are 2 residual space maps that you can see. One of them on the right is the older diffractometer we have with the standard tube. The one on the left is the rotating microfocus anode with the high brilliant source. Now, what you can see here is that the substrate peak is all the way up in this top corner, and that means that all of the layer peaks are completely dislocated, completely relaxed from the substrate, because this is composition. Now, up and down is strain. So if we zoom in, we can see that all of the layers are completely strained but have different compositions. And so in the previous case, we could only see 7 of the peaks, but with our newer diffractometer, we can actually see the 8th of the 9th peak. And another question that people had was, if working in the case of an epitaxial film with a phase that is non-symmetric perpendicular to the surface, how do you determine the direction of the phase with respect to the flat of the wafer? So what these people are asking about is offcut. Now, offcut is very important for thin films because depending on the offcut of the substrate, it can actually affect how your layers that you put on top grow. And so in order to measure an offcut, we essentially are going to do omega scans at different phi. So what that means is that with these 4 measurements, you can determine what your offcut is and also in what direction on the wafer that offcut is from. Now, again, if your wafer has a notch or a flat, we typically use that as the direction of the offcut from that reference point. But if you don't have one of those, the reference point is what you choose it as, and then we, again, can tell you the direction of where that offcut is from. So X-ray reflectivity is something you can also do on a diffractometer. Technically, it's not diffraction, but it's still a very important thin film characterization technique because you can get 3 very important variables about your thin films from XRR data. So we're scanning from 0 to maybe 2-3 degrees at most when we are doing this kind of scan. At the beginning, all of your x-rays are going to be reflected. So we see this flat plateau in the data. When we see this sharp drop, we call this the critical angle. And this is when the x-rays start to penetrate into the sample. And where this density is, so if it's over here versus over here, is going to determine the density of your film. The next thing we think about is after the fact, we're going to have some x-rays that go into the sample and then reflect from subsequent layers and some that are reflecting from the top. And the constructive and destructive interference is what's going to give you these interference fringes. So the slope, if we have a very shallow slope, that's a very smooth sample. If the fringes drop off very quickly, you have a very rough sample. And then the frequency of your fringes gives you the thickness of your film. So if you have several large fringes, you have a very thin sample. If you have lots and lots of fringes, so very high frequency of fringes, you have a very thick sample. So this is something where this is going to be a pattern that you collect, and then you use a program like AMAS is the one we use, and we can calculate a simulated pattern, and then it refines the simulation to your actual data and gives you a goodness of fit with the parameters of your thin film. This is just an example of a thin film that's a hafnium oxide film that's 10 nanometers thick. And again, the red line is done on our standard instrument with a normal copper X-ray tube. And then the blue line is on the newer microfocus rotating anode brilliant source diffractometer. Another question people had was small angle X-ray scattering. So again, not diffraction, but can be done on a diffractometer. So if you have a crystalline material, you're going to see diffraction obviously in your 2 theta, usually above 4 degrees 2 theta. But even if you don't have a crystalline material, if you scan the area between like 0, 2 degrees, sometimes out to 4 degrees, but not that much, you're going to get the X-ray scattering. And the scattering can tell you about a lot about the makeup of the density difference to a matrix, whether you have inclusions or pores, etc. You can learn a lot about polymers and things like that. So we have a Sachs example. These are iron oxide particles in toluene, and this is a small little graphic of kind of what you can get from Sachs. You got size, shape, and surface. And again, this is a simulation-based data collection where you're going to have a computer program simulate a pattern that matches the experimental, which is then going to give you the information like your particle or pore size, which then you can create graphs like this, which gives you your distribution of those particles or pores and things like that. Also on thin films, lots of people ask, how thin can you go? And this is all dependent on the density of your material. So for things like very high Z materials, like a tungsten film, you might only need a 2 nanometer film for us to analyze. We don't really need that thick of a film because the high Z material, your X-rays aren't going to penetrate all the way through it. And when you have low Z material, like silicon carbide film, for example, we typically ask for anything between 30 nanometers and 50 nanometers before we can start kind of analyzing it and getting any kind of useful information out of it. Now, non-ambient and in situ situations. So we have a high temp stage that goes up to 1400 degrees C, and a lot of people were very interested in XRD for battery applications. So we can analyze the cathodes, the anodes, any of the building materials of the battery. We're actually in the works right now to get an in operando stage for a coin cell. So we can essentially be cycling the battery while we're collecting the diffraction. But right now, even without that, we can do battery components. We have a glove box for air sensitive samples. So this is a typical air sensitive sample holder. You would essentially pack your sample in the glove box. There's a sealed O-ring here, and this is just a plastic dome, and the X-rays go through it. It's going to give you an amorphous background, but again, we know the background of the sample holder, so we can subtract that out. And then this is our high temp, HT 1500 high temp attachment for our Rigaku Smart Lab that we use. And as it's named, you can go up to 1500 degrees C, and you can, use it with any kind of atmosphere. You can use atmosphere, nitrogen, argon. You can run any kind of gas you want through the actual oven itself. And then just a couple of specific questions for troubleshooting. So, on what's the best method to strategy or study, analyze highly doped materials that don't have matching reference patterns. So this is something where, again, for qualitative phase analysis, you're fine. You can just say, this material has a structure similar to this one. So you're still going to get your structural information. Elemental information, you're going to need to get from something else, like possibly XRF. And in that case also, if you're trying to do quantitative, you do need to know the specific density and crystal structure of your particular material. And in a research situation, what I would do is try to grow single crystals of the material versus a bulk powder. And I would try to solve the single crystal pattern myself. And that would be the crystal structure you use in your quantitative analysis. If you use Kapton tape, again, it's going to produce an amorphous peak kind of at the lower 2 theta range, but it's not going to cover small intensity peaks, because X-rays are, when you have multiple things, the X-rays are additive. So if you have a large amorphous peak and you have a very small intense peak, that small intense peak will be on top of that amorphous peak because they add. The only issues where you might not be seeing this is if you have kind of a poor signal to noise, where then if you're going to might miss that small peak. So longer collection times, collecting your sample holder with the Kapton tape without the sample in it, so you can do a subtraction, maybe it might help you see that smaller peak as well. A couple of things about standards. So a good question we got was maintaining applicability for a method to quantitate drugs in a formulation, knowing source output diminishes over time. So this person is concerned because let's say we need to analyze a sample and we need to analyze it week after week after week. Well, essentially your X-ray tube is going to lose intensity over time. So the only way to distinguish between your sample deteriorating and losing intensity versus the X-ray tube deteriorating is to use a standard. And you can do internal or external, but what you're going to do is you're going to use your standard and see the drop in intensity and basically subtract that drop from the drop you're seeing in your sample to see and make sure that the intensity drop isn't happening because of your sample. And internal standard methods can overestimate or underestimate your crystalline materials. The reason for this is that the RIR that the program that you're using for your standard is not actually, doesn't have the actual correct RIR. So sometimes it's important to measure the RIR of your internal standard yourself. You can also make sure that your internal standard isn't reacting with your sample and make sure that the peaks for your internal standard aren't overlapping with the peaks of what you care about analyzing. And with that, I'd like to thank everyone for watching. And this is kind of a summary page of just kind of XRD and XRR in general. And with that, I'm going to open it up for Q&A.
Stephanie, that was great. Thanks. We've gotten a number of questions. The first one is, can XRD be used to identify grain boundaries, statistical quantification, average size of grain, range, etc., of grain boundaries and crystallographic orientation?
So for the grain boundaries, when you have different types of grains and different orientations, that's going to be more of, your texture analysis. And in terms of statistical analysis versus in terms of the crystallite size and doing standard deviation, that's something statistical. I guess, Steve, do you have anything to add on kind of details of what you could do to get a lot of the specifics from that list of the question?
Yeah, I guess I'd say the critical thing is that grain boundaries typically don't make up a very high percentage of your sample, and you're at the end of the day, you're going to be limited to about 1 weight percent of material for detection limits. So if there's a different phase in these grain boundaries, there has to be enough of a volume of grain boundaries in order to detect it in a scan that's going to include both the rest of the sample and the grain boundaries. All right, next question is, can you talk about size broadening concepts on quantum dots?
So with the quantum dots, I guess in terms of the size broadening, I'm assuming that means the actual size of the dots themselves. And in this case, we have been kind of working on doing some sacks of some quantum dots and things like that. And yes, you can measure size broadening of quantum dots or any kind of particle in solution, especially with a SACS measurement, and that's going to help you kind of determine what is happening in your particular sample. Steve?
I think I'd add that whether a quantum dot is a single crystallite or not is important. SACS will tell you the size of the particle, but the actual domains that are doing the diffracting might be smaller than that, and that you can tell through the Scherer equation in the crystallite size. So quantum dots typically have very small crystallites, maybe a couple of nanometers. So you have a very broad diffraction pattern instead of these nice sharp ones that we've been showing. There was a question about how do you deal with materials where you don't have enough sample to fill up a sample cup?
So this is where micro diffraction can be very, very useful. So I showed the zero background sample holders. Sometimes we get pharmaceuticals that quite literally only have 2 milligrams of sample. And especially with very, very small amounts of powder, I recommend buying a static gun. If you Google it, you can look it up. It's basically a plastic gun, and if you click it, it gets rid of static, because that's one of the biggest things with very small amounts of powder is your powder will fly everywhere because of static electricity, and you don't want to lose any more than you absolutely have to. So if you dump out little small amounts of powder, if you have a micro diffractometer, you're not going to be losing all of your intensity is going towards analyzing the very, very small amount of powder that you have on your zero background. And you can essentially dump it out, use a static gun so it doesn't, explode everywhere. And if you kind of use like a little spatula, we kind of make a little mound with it. And our diffractometer has a camera, so we can actually do an alignment with the focusing of the camera so that we know that we're aligned in the height of the actual little mound of powder in the center of the sample. And then we make sure with the camera as well that we're hitting the little dot of sample that we want as well.
I think I would just add, for those of you that aren't fortunate enough to have a micro rotating anode XRD tool like ours, putting it on a zero background plate is at least the first step that you should consider. It's quite easy to get milligram level or maybe even microgram level samples to diffract on a regular diffractometer using these low background holders, because basically the only x-rays you're going to see are coming from your sample. All right, the next question is, how do we evaluate mass density from XRD analysis? Do we need separate software tools for the analysis?
So mass density is going to be something, if you're talking about the density of the phases identified, that's something that's going to be inherent to the material. So if you do a phase identification and if you match it to a pattern in a database, it's going to provide you that information. If you're doing density measurements in terms of like a thin film, I would actually recommend an XRR measurement to get the actual density of the film. Can you repeat the question?
Yeah, hang on a second, I have to go back to it.
Yeah, sorry.
That's okay. Was any other software needed to do this?
Yeah, so in terms of software, any kind of software that's going to provide a rebuild analysis capability is going to provide you the density. If you're matching and if you're identifying phases, it's going to have the density involved in that calculation. In terms of, like, again, if you're doing density in a thin film with XRR, that's something that you're going to be refining as a part of the simulation that you're running. So you can start with an approximate value that you can look up online, but then afterwards you're going to try to fit that density to the critical angle of your particular data.
I think I would just add that there aren't many ways that you can determine density besides XRR. Probably the only one that it's not in our lab, but in our facility has physical testing where you can actually use the Archimedes method. If you have a solid material, you submerge it in a liquid and measure the displacement, and you can determine the density of the material from that. So if you're looking at solid chunks, you can get the density that way as well. All right, for the next question is for stress assignment. What if the peak shifts left and right as chi changes? So
Peaks.
Yeah, this one is a little trickier. I would say normally if the peak shifts to the left, despacing is increasing with tilt, and that's tensile stress. You're pulling things farther apart. If the peak shifts to the right as chi increase, or as the tilt angle increases, that's compressive stress. You're smushing those peaks together. If they shift both left and right, I don't know what that means. All right, let's look at another one. Can micro XRD be combined with XCT, X-ray computed tomography, information in the same instrument?
So with CT, I've not personally done it myself. I believe this is not the case, unfortunately. I believe the setup of the instruments are different, and I even think the power of the X-rays is different as well. And so this is something where, unfortunately, you would have to, have two different instruments for that kind of a analysis.
Yeah, I think I would agree that while the basics are the same, you have a source, a sample, and a detector. The requirements are different in X-ray tomography. Your source to sample distance and your sample to detector distance control the magnification factor of the imaging and the resolution of it. So whereas a diffractometer, you want those two distances to be the same. It won't work if you don't. So I'm afraid that the sum of the two is probably not going to be something that happens. The next one is, can you analyze crystal growth on a stainless steel pipe?
So depends on if you want the inside of the pipe or the outside of the pipe. So we require a flat surface, and the reason is because we don't like something called shadowing. And so if you're trying to measure something in like a curve like that, and your x-rays come in this way, they can be blocked by your sample on the other side, and that's bad. We don't like that. So we like something to be as flat as possible. So if you're looking at the outside of the steel pipe, we can probably find, especially if we use a micro source, a flat area to measure that layer of crystallite growth on the top. If you want the inside of the pipe, there's two ways you can do this. You can cut the pipe down so that we get, the flattest, smallest version of the pipe we can get, or we can scrape off the inside of the pipe into a powder and then run the powder.
All right. Let's see. What method is the best method if you have nanocrystalline thin films, especially if you would like to see one of the specific crystalline phases in the film?
Really depends on what you want to know, quite honestly. If it's very, very thin, again, depending on the elements and the density of your film, I'm not sure if it's very, very thin, we might not be able to see the film if it's too thin. In terms of if you want like the first top layer, you could do some kind of grazing incidence diffraction, or we can again do the XRR to get that kind of information from the film, but it's really going to depend on what the film is made of to see if we could do the analysis or not.
Yeah, I would say, it's nanocrystalline. They're going to be broad peaks. Your only chance is grazing incidence or maybe in-plane diffraction, which are very surface sensitive measurements, to try to get as much signal out of the area that you're interested in as possible. All right, we have time for maybe one or two more questions. This one is my Brooker D2 phaser XRD limited in sample type? Why don't I take this one? Okay, go ahead.
Is it a D2 or a Q2?
D2.
Okay, then I'll let you take it.
Okay,
I use Q2s.
This is a tabletop diffractometer. Rogaku makes a version of these as well. You're not really limited in the sample type. The only thing that you're limited in is the power of the X-ray tube is much weaker than the research grade diffractometers that we use. So that means you end up having to collect data for a lot longer than you would on a research grade diffractometer. Otherwise, I think you can use them for anything. All right. With that, I think we'll close the questions. Thank you, Stephanie. If you could go to the next slide. Thank you. So why should you choose Eurofins EAG? Well, obviously, you can see that we have some expertise in what we're doing, but really, confidentiality is the core of our business. We treat all of our customers as if their data is precious and don't allow anyone except you to see the results. I don't really need to read all of these bullet points, but basically, we're the global leaders in testing. We have a wide variety of materials, testing materials, analysts, and expertise. And I think maybe the fact that all of these are available in one place makes it easier if you just are doing XRD. You might need input from elemental analysis or Fourier transform IR or something to get the full picture for your sample, and we have this all in one place. With that, I'd like to pass it back to Rena.
Thank you, Stephanie and Steve, for that robust discussion and presentation. And thank you to everyone for attending today's event. If we didn't get to your questions today, we will be following up with you soon. And if you have any other questions, please send in your questions to the email address on the screen. That is customerservice@eurofins.eag.com. Also want to mention that I've added a few links to our resources in the chat window, along with the registration link to our upcoming Ask the Expert focusing on OJ, TOF Sims, and XPS. So please check those links out. And as a reminder, once you leave today's webinar, you will receive a survey on the presentation, and we would appreciate your feedback. On behalf of Eurofins EAG Laboratories and our experts, thank you for joining us today and have a great rest of your day.